Hello, this is Richard Camacho, and this is video for the second project, ANSYS Fluent Analysis. This is a part 2 from the previous part, which my partner did, which will be linked in the description. Basically, I'm dealing with the analysis of the results of a meter-long flat plate with a 2 meter per second wind gust going over it, analyzing the velocity profiles, the boundary layer thickness, shear stress, skin friction coefficient, and drag coefficient. Basically, beforehand, we set up the geometry, the mesh, setup, calculate the solution, and now what we need to do is analyze the results, which I already have. You open results, and you get this, and I have it open just to avoid loading time to make this video as short as possible. So, the first thing we need to do is pull up the velocity contours and analyze them at the specific range. Now, in order to do that, we are going to insert a contour. We're going to name this bcon. And we're just going to do the domain the location is going to be symmetry 1. Variable is going to be velocity. Click OK. Okay. I got concerned for a second, but just looking at the bottom, although it's hard to see because the actual boundaries themselves are pretty tall. If we were to zoom in, we would see the kind of boundary layer you'd expect from a flat plate where it slowly gets taller and taller until it reaches the end. So from that, we can then make a vector plot named v vector. And then variable is going to be velocity. Scan symmetry 1. Turn this off for now. So the reason the arrows are weird is because my mesh is weird, but I basically wanted as many arrows as possible in this frontal region here, and for some reason it wouldn't let the general mesh work with like a specific inflation I did on the bottom layer. As you can see, the arrows are a lot more dense overall in the bottom layer, and for some reason it wouldn't let me do a quadrilateral mesh in general. But you want to have as many arrows, you don't have as many mesh zones on the bottom so you can accurately get the velocity. So then what we're going to do is we are going to insert a line. I'm going to name this velocity line. And it's going to be 2 points. And this is where we're going to read our velocity profile. So we're going to start at 25 centimeters, which our whole thing is to the scale of from x is equal to 0 to x is equal to 1 in millimeters. So in order to do 25 centimeters, we need 0.25. 0.25. And then for the height, we want to have a relatively small height because so that way we can accurately see the velocity profile and where the boundary layer exactly is and where it kind of maxes out. So let's just say 0.2 for now, and if that's too big, we can always adjust it. Then once we have our line, we're going to insert a chart. Just name this velocity chart. So let's give it V for now, like V25. So that we know it's at 25 millimeters. Our x-axis is going to be, our x-axis is going to be y. And then our y-axis is going to be velocity u. We apply that. Oh, wait. Data series location is going to be on the line. And now if we click apply, I flip them around. It should be, this should be velocity, the x-axis should be velocity u, and the y-axis should be y. That looks better. However, in terms of how our graph looks, it's pretty sharp. So I think we could do it better if we make this a bit smaller. And we could even take more samples if we want to. So we could just say like 25. That is not. Oh. Why did I do that? I don't know. So if I take like 20 samples now. Okay, I'm not gonna come over here. 0.15 is too big for this, so we could do 0.02 and apply it. And that should update automatically, which it does. And this is a much better representation of the velocity profile. Basically, we can see here it starts to flatten out, and it's going to go to 2. So we know our boundary layer is somewhere in this line, and this is a much better representation of what I was looking for. And in order to export this, all you need to do is come over to velocity chart and then click export. And then let's say you want to save it in so what I did is I saved it, and I already have files here saved from I was doing this myself, and the Excel is already set up in advance just so that way there's not a bunch of copy pasting formulas and adjusting text files. I'll show how to do all that in the video anyways, but basically, like let's say you need to save this as a text file, just save it with a name that you remember, so like e25_vid, so that way I know that I'm doing this for the video. You click save. I'm actually going to copy that because we're going to save 3 other files that are very similar. And then in order to iterate this for each height, all you need to do is come over here to the velocity line, edit it, and then you're going to change this 0.25 to 0.5 and apply. And you see it's going to bump up ever so slightly. That means that the change was successful. You're going to come over here and click on the velocity chart, and you can change this to like V50, so that way you know it's 50 from the picture if you need pictures. But realistically, all that matters is that if you export it, that you get the name right here. So like V, I could actually paste my name and V50 vid, and then save that, and then come back to the velocity line and change the 0.5 to 0.75, and then apply it, and then back to the velocity chart, repeat this for V75, and then come back to the velocity line, and this is just gonna be 1. As you see, bumps up again. Come back to the velocity chart. I forgot to make it be 75 for the picture, but it doesn't matter because we're all saving it to this anyways. And the way you would export I'll talk about this more in depth later once we get to the Excel. But the way you export these is basically you take the DAT file and you get like a simple like name of the graph and then just the data. Units are provided, like what it is in its unit. All you really need to do, if you try to copy paste it as is into Excel, it's going to be one cell and you don't really want that. So all you need to do is just delete the space before you delete the comma and the space between the numbers and then press tab. And you repeat that for each individual line of data. For these ones, it's fine, but for the wall shear and the CF, you're gonna have like 80 data lines, and you need to do that 80 times. And that's part of the reason I set up the Excel in advance is because I'm not gonna do all that on the video. That just waste time. So for for the sake of the video not being too long, I'm gonna cut that part out and just have the Excel ready. So yeah, coming back to our analysis, now that we have all of our velocity files, what we need to do next is wall shear. And wall shear is a bit complicated because I can't do it the same way I did the velocity. Because for starters, we need the whole graph, and wall shear is obviously at the wall. So what we need to do is we need to get a line at the wall. So we need to insert a location, and we're going to do a polyline. I'm going to name this wall shear. Okay, that's a reserved name. Shear stress. That works. The domain method boundary intersection. We're going to intersect our symmetry plane, which is like our face plane basically, and we're going to intersect that with the plate, and that creates a line on the plate. So we click apply, and here we have our shear stress line. We're going to insert a chart. We're going to name this SS for shear stress. And then for SS, our data series is going to be on the shear stress line. Our x-axis is going to be wall shear at, we'll just make it wall shear, make it easier. Our y-axis, well actually our y-axis should be wall shear, and then our x-axis should be x. And if we click apply, should get something that looks somewhat like this. Basically, our wall shear at the very beginning is really high because the way the formula works is that shear stress is equal to the viscosity times du dy. And as you can imagine, when du dy, when not du dy, when when u is 0 and then it changes to something at a relatively short distance, the du dy is going to be very high at the beginning, which is why we see like a really sudden drop off, is because du dy is going to instantaneously drop off, and then the decrease is going to parallel. The decrease is going to plateau, and what happens is this value approaches 0, but it never really reaches 0 because du dy's decrease is the derivative of du dy is going down. The rate of change of du dy is lowering, which means that the graph is going to plateau. And once again, export, make it a text file, save it as whatever you need to, shear stress, vid, and save. Boom. So, moving on to skin friction. Skin friction is a direct formula of the shear stress. So we can use the shear stress data to get the skin friction coefficient here. Now the formula is, oh, I closed that. We're back. Looking over the syntax for the formula I was trying to put in, I forgot to make this a capital I, which means that now we're actually doing a proper function. This is supposed to be wall shear, specifically in the x direction, and we're supposed to signify where we're doing it at, which is at plate underscore, which is the name of the name we have for the plate. Click apply, and we get a value. Now, in order to get the drag coefficient, we need to make another variable, drag force. I did not make that the right name. Drag coefficient. That is going to be drag force divided by the 1/2 density free stream velocity squared again. 0.5 times 1.2 times 4. And there we go. That's our drag coefficient. Once we have all these values, and once we've combed through all of them and erased all of the commas for even the wall graph and the skin friction coefficient graph, what we can do is we can go into an Excel graph and put all of those values in. So for instance, this is the Excel I set up before making the video, so that way I wouldn't have to go through all of this, because this is pretty repetitive, and basically all you do, copy paste the data, make a symbol that lets you know clearly what it is, and you repeat that for shear stress, skin friction, and your drag coefficient. For velocities, I also have like the distance in meters that each of the dots are at, so we can plot them clearly. Here is our boundary layer. So for the graphs, we need two things. We need for velocity, we need the profiles, and we need the theoretical boundary layer thickness at each height. So for this, the formula is 5 times the velocity, which is here. Oh wait, no, 5 times x. 5 times x over the square root of the Reynolds number, the local Reynolds number, which is the density times the velocity of the free stream times x divided by the viscosity. So we get the boundary layer, the hypothetical boundary layer thickness for each distance along the flat plate, and then we compare them. The way I made these graphs is it has two legend entries. There's the velocity profile, which is this entry here, and then there's the boundary layer thickness, which is this entry here. So then you click OK, and you repeat that 3 more times. Like for this one, the velocity profile, that's this data. Like if I wanted to make one right now, what I'd do, let's say I wanted to make the velocity at 50 centimeters, I go to insert, and we insert a smooth curve graph, and then we click on it, and we go to select data, and then we add a series, and we're going to name this bound, and the x values are going to be this, the y values are going to be the y thickness, and these should be the same value because it should be a straight consistent line that clearly separates where the velocity profile is forming to where it is all uniform. So if I click OK, and the x values have to be 0.0 to 2.1, just basically where it just to where it intersects. And let me click OK, and there we have our line that separates the two regions. And of course, like if you want to add axis titles or a legend, change the titles to make them proper, change the series title, you go to select data and you click edit, change the series name. But for the sake of this video not being too ridiculously long, I already have all that done, so I can just delete this graph. This is an ANSYS tutorial, not an Excel tutorial. So, from what we can see on with these graphs, this isn't exactly the best method to tell because there's no clearly defined boundary point with the fact that it only takes 10 points. But we can see that for all of the graphs, there is a maximum distance outwards. There's a maximum velocity, which is seen, and then where it sort of goes, the velocity goes down a bit as it approaches the 2.0 meters per second of the free stream. And where this maximum is where the boundary layer is. As you can see, for all of the graphs, the theoretical is very accurate with the graphs given by ANSYS. Moving on to shear stress, basically all I've done is I've taken the analytical, graphed it out. Same thing with the velocity. I took the analytical, graphed it out, and then made a list of theoretical values and matched the horizontal. I matched this column with this column to get the orange line. Basically, this formula, it is 0.322 times the viscosity to the power of 1/2 times the density to the power of 1/2 times the velocity to the power of 3/2 divided by x to the power of 1/2, which is obviously column A. So we get these values, we graph them against each other, and as we can see, the two graphs are very similar. The only real big difference is this little, for the theoretical values, the graph is a little sharper in this corner than, say, our ANSYS values. Overall, they match. Moving on to skin friction, obviously, since we put skin friction in terms of shear stress, because it's shear stress over a constant number gives us our skin friction coefficient. The skin friction coefficients should look very similar, and they do. As we can see, the same thing here. The theoretical values have a bit more of a sharper bend there than the ANSYS values. And as you can see, the formula is 0.664 over the square root of the Reynolds number, the local Reynolds number. So those are constant with each other. Moving on to the drag coefficients. Here we had a very significant error. Theoretical comes out to be 0.003 and the ANSYS value comes out to be 0.0002. Now, as for why this happens, there could be any number of reasons. Maybe, for instance, the drag coefficients don't really work well on ANSYS because of the particular mesh I had, or there's some sort of error in the way I calculated the drag coefficient value. It could be any sort of reason. But these values should come out to be relatively similar. As we can see with the rest of our graphs, there have been, like the theoretical have and the answers have held pretty closely. Not exactly perfect, but they've all held relatively closely. And drag coefficient should come out to be roughly equal. And that is all for this project. We have looked over going into the results tab of ANSYS and analyzing it in terms of how to make a contour plot, how to make a vector plot, making graphs based on data by making a line and then using that line to plot our velocity profile, interpreting the velocity profile, seeing where the boundary layer is, exporting everything to Excel, using formulas provided to make theoretical graphs and to compare these graphs. And last but not least, calculating a drag coefficient, which is just completely wrong. That is all. Make sure to like and subscribe.